Rust in AI Masterclass by Edgar Milvis Volume 1, Chapter 1. The borrow checker meets tensors, avoiding clones. At its heart, Rust's ownership system is a compile-time resource manager. Imagine a library where books, data, are stored on shelves, memory. In traditional systems programming, like C, you have a librarian who gives you a slip of paper with the shelf location of a book. You can read the book, but if the librarian decides to move that book to a different shelf while you are reading it, or worse, throw it away, you are left with a pointer to nowhere, a dangling pointer. This leads to memory corruption or segmentation faults. Rust solves this by assigning every book value a unique owner. When you check a book out of the library, bind a value to a variable, you are the sole owner. You can read it, and if you want to let someone else read it, you can lend it to them, borrowing. However, the library has strict rules. One owner at a time. You cannot give the book away while you still need it. If you transfer ownership, move semantics, you lose access to the book. 2. Borrowing rules. You can have either 1. Mutable borrow. You can lend the book to one person who can write in the margins, mutability. Many immutable borrows. You can lend the book to many people simultaneously, provided no one writes in it, immutability. In the context of AI and large tensors, multidimensional arrays representing weights, activations, or datasets, these rules are not just safety features, they are performance optimizations. Copying a tensor, a book, that occupies gigabytes of memory is prohibitively expensive. The borrow checker acts as the librarian that prevents accidental duplication. It enforces the rule: if you need to read the data, look at the existing book. Do not photocopy the entire library unless absolutely necessary. Now, let's talk about the cost of cloning, the photocopier analogy. In AI workflows, data flows through pipelines, pre-processing-augmentation-model inference-post-processing. In languages without ownership semantics, the default strategy to ensure data safety is often defensive copying. If a function needs a tensor and isn't sure if the caller will still need the original, it makes a copy. The analogy: imagine you are a chef, the function, preparing a dish. You are given a crate of vegetables, the tensor data. To be safe, you send the crate to a photocopier to create an identical duplicate before you start chopping. If the crate contains 10,000 vegetables, this takes significant time and warehouse space. The AI reality: a single parameter matrix in a modern large language model, LLM, can be hundreds of megabytes. Copying it just to pass it to a layer calculation is a waste of memory bandwidth and cache efficiency. It doubles the memory footprint, potentially causing out-of-memory (OM) errors on GPUs. Rust's borrowing allows us to pass a reference, a lens or a view, into the function. The chef looks at the original crate through a magnifying glass. No duplication occurs. The borrow checker guarantees that while the chef is looking, reading, no one else will throw the crate away or modify it underneath them. To manage tensors efficiently, we must distinguish between owning the data and viewing the data. 1. Owning structures, vec-t, tensor. These manage the memory lifecycle. They allocate memory on the heap and free it when they go out of scope. 2. View structures, and t, and tensor. These are borrowed references. They contain a pointer to the data and a length, or shape, but they do not manage the memory. In AI, we often need strided views. A tensor might be stored contiguously in memory, but we want to access a slice, a transpose, or a specific channel without copying the underlying data. Now, let's explore lifetimes, the expiration dates. Lifetimes are the annotations that tell the compiler how long a reference is valid. In the library analogy, a lifetime is the duration of your library card. You cannot access the book after your card expires. In tensor operations, lifetimes ensure that a view into a tensor does not outlive the tensor itself. Scenario: we have a training batch struct containing the data. We pass a reference to this batch to a forward pass function. Constraint: the forward pass result, which might contain intermediate activations, must not outlive the training batch. If the training batch is dropped, memory freed, the activations become invalid pointers. The borrow checker links these two lifetimes. It forces the programmer to structure their code such that the data provider, the batch, lives longer than the data consumer, the forward pass. Now, let's explore the clone on write pattern, the lazy photocopier. Sometimes, we need a function that can accept data that is either owned or borrowed, and it only needs to modify the data if necessary. This is where std borrow a cow comes in. The analogy: imagine a reference manual. You need to annotate a page for a project. Scenario A: borrowed. The manual belongs to the library. You are allowed to write notes on a separate piece of paper attached to the page. You don't need to own the book. Scenario B, owned the manual is your personal copy. You are allowed to write directly in the margins. Cow A T is a smart pointer that can be either borrowed and AT or owned T. It abstracts away the decision of whether to clone or not. Why this matters for AI, data augmentation: you have a dataset of images. You want to apply a random brightness filter. If the brightness change is 0, identity, you return the original borrowed reference. If the brightness changes, you must clone the data, modify it, and return the owned version. Cow allows the API to return either without forcing the caller to handle two different types. Now, let's talk about visualizing data flow with and without borrowing. The following diagram illustrates the memory flow in a typical AI pipeline. Notice the distinction between the logical flow and the physical memory allocation. The diagram contrasts the logical flow of data through an AI pipeline with the physical memory allocation, highlighting how Rust's borrowing system manages memory ownership and references to prevent data races and optimize performance. Moving on to systems analogy, Arc Mutex T versus file locking. To understand how Rust handles shared mutable state, which is common in training loops where multiple threads might access a parameter server, we can compare it to operating system file locking. In distributed training, we often have a shared model state. The C++/Python approach, Arc Mutex T in many languages, shared mutability is the default. You wrap data in a mutex, a lock, to prevent data races. Arc, atomic reference counting, keeps the data alive as long as any thread holds a reference. Analogy: this is like a file server where a file is locked. If thread A holds the right lock, thread B must wait. If thread A crashes while holding the lock, the file might remain locked, deadlock, or the data might be corrupted if not handled carefully. It requires runtime overhead, atomic operations for reference counting, syscall for locking. The Rust approach, ownership and borrowing: Rust's type system enforces that you can only have one mutable reference or many immutable references at compile time. Analogy: this is like a library with a strict one writer, many readers policy enforced by the librarian before you even enter the reading room. If you try to enter the room with a pen, mutable, while someone else is reading, the librarian stops you at the door. There is no runtime locking overhead because the check happened at compile time. Connection to previous chapter: in the previous chapter, we discussed memory layout and stack versus heap. We learned that heap allocation, box, vec, is expensive. Arc adds further overhead because it requires an atomic increment/decrement of a reference counter on every clone or drop. By using borrowing, we avoid both heap allocation and atomic operations, keeping the data on the stack or in the original heap allocation, accessible via a lightweight pointer. Now, let's explore designing APIs for maximum reuse. The theoretical goal of this chapter is to design APIs that are agnostic to ownership. Now, let's explore the deref coercion mechanism. When we implement a custom tensor struct, we want it to behave like a slice of data when passed to functions expecting raw data. Rust provides the deref trait. Concept: if you have a type myTensor that implements deref target satface f32, Rust will automatically convert A and myTensor into A and f32 when passed to a function. Analogy: this is like having a specialized bookbinding, the myTensor struct, that contains extra metadata, shape, strides, but when you hand it to a reader, they don't care about the binding, they just want to read the pages, the slice, f32. The language automatically unwraps the wrapper to expose the underlying data interface. Now, let's talk about the asref trait for explicit conversion. While deref is for smart pointers, asref is for general type conversion. It allows a type to be converted into a reference of another type cheaply. Why use it? It allows functions to accept not just in tensor, but also in vec f32, and f32, or and u8, for raw byte parsing, without changing the function signature. This makes the API flexible enough to ingest data from various sources without copying. Now, let's explore the cow strategy in API design. When designing a function that might need to modify data but prefers not to, notice how the function signature at line 2 uses a generic lifetime A and the cow smart pointer. This is a critical architectural choice for memory efficiency. We accept a cow clone on write type, which can hold either a borrowed reference or an owned value. The type cow f32 means we have a slice of f32s that may or may not be owned by this function. At line 3, we perform a check to see if the data is already normalized, values between 0.0 and 1.0. If this condition is true, we avoid any memory allocation whatsoever by returning cow borrowed at line 5, which simply wraps a reference to the original data. This is extremely efficient because we're not copying potentially large datasets. If we had used a standard vec parameter, we would be forced to allocate memory even when no modification is needed. The implication here is significant. In production AI systems processing millions of embeddings, this pattern can reduce memory pressure and GC pauses by orders of magnitude. When the data at line 3 fails the normalization check, we enter the else block where we must modify the data. At line 8, observe the use of input.into_owned. This is the right part of cow's clone on write behavior. If the input was already owned, e.g., passed as an owned vec, into_owned is zero cost, it just returns the existing owned data. However, if input was borrowed, a reference to external data, this method performs a clone, creating a new owned copy. This lazy cloning is crucial for performance because we only pay the allocation cost when modification is actually required. At lines 9 to 11, we perform the normalization transformation in place on the owned data. The formula, *x 0.5/2.0 maps the data from whatever range it was into the 0.0, 1.0 range. Finally, at line 12, we return cow owned, transferring ownership of the modified data back to the caller. This pattern is superior to always cloning immediately because it gives you the best of both worlds, zero copy when possible, automatic cloning when necessary. Without this pattern, you'd need to manually check and branch your logic, leading to more complex and error-prone code. This pattern is crucial for lazy evaluation in data pipelines. It ensures that memory is only allocated when strictly necessary, preserving the zero-cost abstraction philosophy of Rust. Now, let's explore theoretical foundations. The theoretical foundation of avoiding clones in AI rests on 3 pillars. 1. Ownership. Memory is tied to a variable scope. Moving data prevents accidental duplication. 2. Borrowing. References allow temporary access without taking responsibility for memory management. 3. Lifetimes. The compiler verifies that references never outlive the data they point to, eliminating dangling pointers. By leveraging these features, we transform memory management from a runtime burden, garbage collection or manual-free, into a compile-time guarantee. This allows us to build AI systems that are as fast as C++, no runtime overhead, but as safe as high-level languages, no memory errors, specifically optimized for the large data movements inherent in tensor operations. Now, let's explore basic code example. This example demonstrates a high-performance scenario, an inference server processing a large input tensor, e.g., a 3D image volume, and running multiple lightweight operations, slicing, normalization, on it. We will define a tensor struct that owns its data and a TensorView struct that borrows data from a tensor, or any slice, without copying. This leverages Rust's ownership system to ensure memory safety while maximizing performance. Let's discuss the code. Notice how we define the core data structures here. The tensor T struct at line 11 is the owner of the data. It uses a vec T for the data buffer and a vec usize for the shape. This is a classic ownership pattern in Rust. We use number_traits afloat at line 5 to enable generic numeric operations, meaning our tensor can handle F32, F64, or other float types. The shape vector is crucial because it defines how to interpret the flat data buffer. If we didn't store the shape, the data would be meaningless. This design is efficient for storage but requires careful handling when we want to avoid copying data for operations like slicing. Here we define TensorView at line 22, which is the cornerstone of memory efficiency in this design. Unlike Tensor, TensorView does not own its data, it holds a reference NA, T. The lifetime A is critical, it ties the view's existence to the lifetime of the original tensor it borrows from. This is how Rust prevents dangling pointers. We could have designed this without views, forcing us to copy data for every operation, but that would be disastrous for performance with large models. By using a borrow, we achieve zero-copy operations, which is essential for high-throughput AI inference. Look at the new function for tensor at line 32. A key decision here is the assert_eq at lines 34 to 40. This is a safety check to ensure the provided data length matches the product of the shape dimensions. Without this, we could create a tensor with an inconsistent state, leading to out-of-bounds access later. In production, panicking might be too severe, we might want to return a result tensor error instead. However, for this demonstration, the assertion clearly communicates the invariant. This function is the only place where a tensor is created, ensuring all instances are valid by construction. The view function at line 46 is extremely important for the system's architecture. It returns a tensor view that borrows the entire tensor. Notice the operation count, it's 1, because it just copies references and the shape vector. It does not iterate over or duplicate the potentially massive data buffer. If we were to implement this by copying the data, the performance would degrade linearly with the size of the tensor. This function enables the run_inference_step to operate on the tensor without taking ownership, allowing the original tensor to be used elsewhere after the inference step. The slice method at line 57 demonstrates the power of Rust's borrowing system. It creates a new tensor view that points to a subregion of the original data. Look at lines 58 to 60. We calculate the start and end indices in the flat buffer based on the shape. This is where understanding the tensor's memory layout is vital. We assume a row major layout. By slicing, we can process a batch of data, e.g., slice 0, 1, for the first batch item, without moving any data. This is how frameworks like PyTorch or TensorFlow handle subtensors efficiently. Without this, we would need complex indexing logic in every operation. Implementing DREF4 TensorView at line 76 is a subtle but powerful ergonomic choice. It allows us to use a TensorView as if it were a standard slice and t. This means we can call all the standard slice methods, like iter, len, or indexing, directly on our view. Notice how run_inference_step at line 94 calls input.iter. This works because deref coercion turns in TensorView into n_t. If we didn't do this, we would have to write input.data.iter, which is less clean and couples the function to the view's internal structure. The run_inference_step function at line 87 is designed to be generic and efficient. Notice the trait bound t, float plus std, fmt debug. This constrains t to types that support floating point math and debugging, which is exactly what we need for this calculation. The function accepts in TensorView t, meaning it takes a borrow. This is the architectural key. The function is decoupled from data ownership. It can operate on any view, a full tensor, a slice, or even a hypothetical future view into a GPU buffer. The calculation of the mean at lines 94 to 95 is a good example of using the deref implementation to iterate over the data slice. In the main function, look at lines 102 to 113 where we set up the data. We create a vecf32 and then move it into tensor_inu. Notice that after line 112, the data variable is no longer usable because ownership has been transferred to input_tensor. This is a fundamental Rust concept. The shape vec 2, 4, 4, 3 defines a 4D tensor, common in AI for batch processing. In a real system, this data might be loaded from a file or received from a GPU. Here, we simulate it, but the memory management principles remain the same. Lines 115 to 132 show the core workflow of zero-copy operations. At line 118, full_view is created. At line 122, we pass it by reference to run_inference_step. Notice that input_tensor is still fully available after this call because we never transferred ownership. Then, at line 126, we create slice_view. This is a view into just the first batch item. When we pass slice_view to the inference function at line 131, the same function logic operates on a fraction of the data, but without any data copying or function recompilation. This demonstrates how to build scalable processing pipelines. Look at lines 133 to 135. When main ends, input_tensor is dropped. Because full_view and slice_view are borrowed from input_tensor, Rust's borrow checker ensures they cannot outlive the owner. This is enforced at compile time. Without this safety net, we could accidentally use a view after the underlying data is freed, leading to use after free bugs. In a production environment, this compile time guarantee eliminates an entire class of memory errors, making the system significantly more robust and secure. By scanning this code, you go on the details on leanpub.com. By scanning this code, you go on the details on amazon.com. This code bring you to the source code repo on github.com. Thank you for your attention. This lesson is excerpted from Volume 1, Chapter 1 of the Rust in AI Masterclass ebook series and from the volume Advanced Memory Patterns for AI. You can find all the details here, https://github.com/edgarmilvis/rustai programming series. The ebook also includes 20 chapters with diagrams, advanced examples, and 5 exercises with solutions. I look forward to seeing you in the next lesson.